Hello and welcome back to another Rust video. Today we're looking at the atomic reference counter type. This is a smart pointer that enables us to count references. And you might wonder, when does this actually make sense given that Rust has the concept of ownership? So this is going to be an interesting one. Let's have a look at that. Okay, as always, I've already executed rustling's watch inside of the rustling's repository. And if I scroll up here, we can see that there is a bunch of errors here in standard library types arg1.rs. And I'm just going to go ahead and open up that file right away. So I'm going to open up exercises, standard library types, and then arg1.rs. Okay, so the file says, make this code compile by filling in a value for shared numbers where the to-do comment is and create an initial binding for child numbers somewhere. Try not to create any copies of the numbers vector. And yeah, that's pretty much it. Okay, and then here, there's a bunch of things going on that you may or may not be familiar with. So let's just quickly go through what's going on here, and then hopefully we can demystify what this arg type is all about and why we need it in the first place. Okay, so we have a vector of numbers, and we're seeing here that the code uses the range expression syntax here to create a range of values, which is iterable. That's why we can call collect on it, and it creates a vector at the end of the day. Then we have this shared numbers thing here that we need to do something with, and then we have another vector of something that is called join handles here. This is going to be an important one in a second. And then we have a for loop where we're iterating over some numbers from 0 till 8. And for every iteration, now this is interesting. In every iteration, the code goes ahead and creates a new thread. So if you're not familiar with threading in Rust, don't worry about it too much. I'm probably going to cover it in another video. For now, I'm just going to give you what you need to navigate through this code. So we have this vector of join handles, and we push in whatever this code here returns. And what that code returns is a join handle. A join handle is something that we get whenever we spawn a new thread. And this is what's happening here. So as we iterate over these numbers, we spawn a new thread, and then we give it this function here that is being executed. So this is how we send code through another thread for execution. And for every thread, what we're doing is we're taking an offset, which is the number that we're iterating over, and then we iterate over the length of the child numbers array, which we haven't created yet, but we can assume that this is obviously a list of numbers. And then we add whatever value we get from this inner iteration out of that child numbers array, and we add it to the sum of the variable that we've defined up here. And then we increment our outer counter, our offset here, by 8. So in the first iteration, I is going to be 0, and then it's doing its work here. And then in the next iteration, it's going to be 8, and it's going to do its work. And then in the next iteration, it's going to be 16, and so on and so forth. And then also in every iteration, what we do here is we output the sum of the offset that we calculated. Now, once all of that is done, basically once we've spawned a bunch of threads that are doing some work, we have this vector of join handles, which is what we get from these threads, and we can use them to close the threads again. And that's exactly what we see down here. For every handle that we have, so here we have our join handles vector, and we turn it into an iterator. We do that so we can iterate over it, obviously, inside of the for loop. We call join on the join handler. And that's the method that we use to get whatever return value is produced by that thread and pass it back to the parent thread again. And this is returning a result. That's what we call unwrap here. So keep in mind that in theory, this might as well produce an error in case the thread wasn't successful. And then the code is done. So again, the bottom line is we're iterating over a bunch of numbers. For every iteration, we create a new thread. We do some calculations there, and then we close the thread and output some values. Okay, now back to the actual task. What's the issue here? Now we've seen that there's this thing called child numbers, which doesn't have any definition here. Let's change this code just for the sake of the example here and say that these threads here are not actually working with the child numbers variable, but with the numbers variable that we have here, the one that is already defined up here. And look at the code again. Now, due to Rust's ownership model, this is not going to compile, right? So we have a vector of numbers, and as soon as we create this thread and we're using this numbers variable inside of the thread, we're actually passing ownership to that thread. In fact, this is exactly why we have this move statement here. So this move expression, it explicitly says we're going to pass ownership of whatever is happening inside of this function to that other thread. If we consider that there is multiple threads being spawned at the same time, there would be multiple threads that need access to this numbers vector. And again, Rust doesn't allow that because of the ownership model, right? Only one variable can own a value. And because there's scenarios where this is the case, Rust gives us a type, or actually two types, that allow us to do reference counting. For scenarios where we just need to have a value around as long as it needs to be, namely, as long as there's code referencing the same value, that's the lifetime of that value, no matter where it is. And these two types that Rust provides are the arg type, which is an acronym for atomic reference counter. And then there's also the normal reference counter. So in other words, there is actually the reference counter of type T, and then there is the arg counter of type T. Now, these are pretty much exactly the same. There's just a minor difference in implementation that the normal reference counter is assumed to be used in non-threaded programs. So it's a little bit faster, but you can't really use it in code like the one that we're dealing with, where we're creating threads and there's multiple threads that need access to that reference counter. And the arg actually comes with that capability to have a reference counter that works over multiple threads. But what does a reference counter do? So if we look at a reference counter, it's really just a smart pointer, just like a string or a boxed smart pointer. Those two types we've talked about in some of the previous videos that I'm linking up here. And they're really just a smart pointer with a reference count. And whenever we create additional references to the same value using that reference counter, the counter is incremented. And then the cool thing is, as soon as a reference counted value goes out of scope, the reference counter gets decreased automatically. So you don't really have to worry about cleaning up after yourself. Now, we can make use of that in this code by not actually passing ownership of the actual values of our numbers to the thread, but a reference, and we can use a reference counter for that. Okay, so this is what it looks like. So we have this shared numbers variable here. Now this is just going to be an arg new and then of numbers. So this is going to create an atomic reference counter that points to this vector, but it has a reference counter in it as well. And then in here, what we can do is remember that here we actually had child numbers down here and child numbers down there. And this is a variable that actually doesn't exist in this program yet. We have to introduce that. In this particular case, we need to create child numbers outside of every single thread because it's supposed to be a reference to the numbers that we're dealing with. So here we want to say for every iteration, we create a new variable child numbers. And child numbers is going to be a clone of our initial shared numbers. Obviously, up here, this has to be numbers, not number. Okay, so now what this does, it's obviously cloning the value that we're dealing with, but it's actually not doing a deep copy of the data. It's just creating another smart pointer that points to the same data as the original one, and it's increasing the reference counter that it comes with. Now, this child numbers variable can safely be passed to this thread here, and when it goes out of the scope, it's just going to be dropped and freed up from memory. And that's no issue because for every single iteration, we create a new child numbers reference using the reference counter. And that should make the code memory safe again. Okay, so let's save that and see what the compiler says. Okay, cool, this works. And here we can also see that the numbers that we're iterating over are actually not executed in order. And that's because we're dealing with threads here. And with the code that we have, we can't actually guarantee the order in which they're executed or in which they're finished rather. And that's why we see that the offset here is not going from 0, 1, 2, 3, 4, 5, 6, 7, but it's actually a little bit out of order here. 0, 2, 1, 3, 4, 5, 6, 7. Okay, I'm gonna go back and removing this comment to head over to the next exercise. And that was the little introduction to atomic reference counters. Hopefully that gave you a little bit of an idea when reference counters are needed in Rust. And make sure to check out the documentation as well if you want to dive deeper into that topic. Thanks for watching.